Hi, my name is Lopez Caniego. I'm an astronomer at the ESASky Science Data Center, and together with my colleague and software developer Matthias Wonblad, we will be walking you through the talk Exploring the Universe with ESASky's JupyterLab widget. At the European Space Agency, over the years, several space missions have been observing the universe, and the data from these missions is hosted at the European Space Astronomy Center near Madrid, which also hosts the science operation centers for many of these missions. At the ESASky Science Data Center, we have developed a tool called ESASky that allows astronomers and the general public to discover the archival data for many of these missions, not only from the ESA, but also from other data providers like NASA, the Japanese Space Agency, and ground-based observatories. To complement ESASky, we have developed the JupyterLab widget that is called ESASky. And I will be doing a demo very shortly about this. Example notebooks illustrating the capabilities of ESASky can be found in our GitHub repository. So now let me go directly into the demo. First, we import all the necessary modules. ESASky can be installed very easily with pip, as this is explained in the GitHub repository documentation. Now we instantiate the widget. And let's start. This widget gives the user control of the web application. So you can change the targets, you can change the field of view, for example, or go to a different position of the sky based on some coordinates. You can also change the background images. In this case, I'm going to show you some images now. This is in the optical from the Digital Sky Survey. And then we are navigating from the near infrared from TUMAS, the mid infrared from WISE and Spitzer, and the far infrared from Herschel. You can also query the database for objects in the sky within some circle. So in this case, we are going to query the Herschel catalog, 4-point sources, and now let's center on it. We can also query for observations. For example, for Chandra observations in the same field of view, or from spectra. We can also interoperate with external data providers using the Table Access Protocol tab. So in this case, let me move to a different position in the sky. Let's see what are the available tab services. In this case, we have access to the European Southern Observatory, the Canadian Astronomical Data Center, and the Mikulski Archive in the Space Telescope Science Institute in Baltimore. So let's see what is all the data that is available for these missions. So we have lots and lots of ground-based observations and space data. In the particular case of the European Southern Observatory, we are now querying their tab servers. So we have this for the very large telescope in Chile. We have access to the data, all this data. So now let's dump some of this data in the interface. Here you can see the footprints for all this data. You can recenter, and just by clicking on this access URL, you will be sent to the actual archive. You can also get this data in a table if you wish to. And now let's move to the next functionality. You can overlay footprints on ESASky. So now let's go to this Spitzer data, and let's load some footprints of the observations that could be private observations that we have in our own disk that are not yet public. So I can overlay them and look at them and interact with them. And we can also, before I was showing you that you can navigate through different heaps, which you can also load multiple heaps at the same time. So by doing this, if I open the panel, I see all these Spitzer, Chandra, XMM, DSS, TUMAS data loaded. And now we can navigate through it. Let's zoom in a bit. You can go from one to another, and this gives astronomers the possibility to understand the physics that is behind this object across wavelengths. Now, Now let me show you one more functionality, that is the observation planning tool. So this is a tool that allows astronomers to prepare observations. At the moment, it only has information for the James Webb Space Telescope that will be launched next year. In this case, I will be showing all the footprints for all the instruments on board James Webb. And you can, in this panel, you can turn around, move around, and then this information can be saved to a file and then used later for your observation. So now let me give the floor to my colleague Matthias. He will be telling you a bit about the actual development of the widget.
Thank you for that, Marcus. So my name is Matthias Wångblad, and I work as a software developer at ESASky, and my part of this presentation will be discussing the behind the scenes and the coding of ESASky, and specifically how we solve communication between Python and the web page that we use. So ESASky is based on 3 parts. The first 2 parts, the Python and JavaScript, is based on the Jupyter Widgets, which is developed by the Jupyter team, just for stuff like this, so we can enable having the web page inside Jupyter. The Python part is, of course, the access point for the user, and the code here is mainly focused on just transferring the functions into messages that we can use in the web page. The JavaScript part is where we use the IP widgets to be able to actually embed this web page inside an output view. We do it with this code here. So we add the web page inside an iframe, which can then be used in an output. And the actual web page, of course, is the final part, which is where most of our actual development is. And of course, the communication in between here is a very important factor. So between the Python and JavaScript, all of this is enabled through the IP widgets, which uses the same WebSocket as Jupyter used for any communication between what you can see on the screen and the actual Python kernel. And between JavaScript and the actual iframe web page, we used HTTP messages. Because this enables us to have a single entry point for our API in the web page. So wherever we want to use ESASky, we can use the same commands to control it. And we don't run into any issues with cross-origin or similar. So here you can see a quick code snippet inside the JavaScript, where we actually listen on a custom messages along the WebSocket from the Python kernel, pass along the exact same message as an HTTP message. We post it to the iframe, the currently active iframe, which we want to receive the message. And then we also have an event listener to listen for messages from the iframe and those who send along with the IP widgets infrastructure on the WebSocket back to Python kernel. We have a page describing all of the possible messages that can be sent over our API on this page. So for example, if we want to go to Orion and set the field of view to 4.5 degrees, you can see how this works, like that. The JSONs that is passed along as the HTTP message will look like this. So this is what actually being sent to the ESASky page. So now the tricky part in the communication was to actually get the Python code to wait for response from a web page. For example, if we want to check what missions have any observations and how many observations they have in this part of the sky, we have a command for this, get observations count. Now we also want to put the response from this in a Python variable and do something with it. Here we just pass it in pandas to make it look a bit better. So the problem here is that all of these 3 instances run on separate processes with separate job queues that have no knowledge of each other. By default, the Jupyter kernel doesn't check the message queue until all cell computations are finished and the kernel is idle. So in order to actually get the message back inside the cell, we had to set up our own function to check all of the message queue to see if any incoming message match the one that we expect to see. So whenever we send a command where we expect to get a response, for example, like get observations count, we use this function that we created. So after we sent it, we start looping until we reach a timeout in case something goes wrong. And check this 10 times every second, loop the message queue, and try to see if any of the incoming messages in the WebSocket matches the message ID that it should have. In that case, we actually return the value and parse it, and we get the response from the web page. So if we actually run the computations of this cell, we can see that we actually get something back from a web page. We can see that we, for example, have 10,000 observations in total in this area, and that we have 40 of them are through Chandra, which is one of the emissions that we show in ESASky. We can also, of course, do more stuff. We can plot the observation and actually get the data that we have here. You can see that waits for until the data is actually fetched from the database, and then we can read it in here, and here we plot the first 3 of these metadata to actually see the data here and use it, and we can do all sorts of data manipulation, of course, afterwards. Finally, if you want to use ESASky, it's available on PyPy, so you can install it through pip with pip install ESASky. And if you also want to use in a JupyterLab, not just a notebook, you will need to install the lab extension, which is available through npm with this command. And thank you for your attention. I know this is also a very quick presentation. If you have any questions, don't hesitate to contact me. My contact details can be found in the beginning of the presentation. And I thank you all for your attention, and I hope you have a very good day. Bye.